So I'm going to say now, if this is right, it follows that the integral we get for the magnetic field has to give us this, right? So the integral for the magnetic field is what? Let's write it out coherently, factoring out all the constants. You got K prime, A. Why do I have delta L in there? Oh man, we got to go back and look at that integral real quickly. It should have been a delta X, not a delta L, because that is your delta L, right?
Yeah. Right.
Or the integral should have been with respect to L. I'm going to leave L in there. Okay. No, I can't do that. We'll modify what I did, very simple modification. And I forgot my K vector, but I'm going to slip it in. Now that's for that integral. That's the K vector, but that depends on the coordinate system. Okay, so then it's going to be x star, x squared plus a squared to the 3/2. Now let's go back and see what didn't make sense in what I did previously. I had a delta L here, right?
Yeah.
Right. Yes.
Okay. Well, I don't really want to talk about delta L. That's really a delta X, because now we've got an x-axis, right? So I could change that to a delta X, I could change that to a delta X, and so forth. But starting here, I'm going to replace my delta L with a delta X, right? So now I've got delta X here, delta X here. And now when I approach the limit, delta X becomes the dx, right? Because I didn't do that real carefully. If I'd have done that carefully, you know, filled in the little details, I'd have caught it at this point. Got used to using delta L, kept it. So watch what I do and do it right. Okay? So that would be our integral, and we don't have a delta L here anymore. Okay? Because our delta L in the limit, well, from here on, delta L is a delta X. Okay. Again, that gives us a dx. Okay? So, again, our conclusion here, if Ampere's law is correct, this integral should give us 2k prime I over A. Okay? Now notice, we're integrating the reciprocal, essentially a reciprocal cube of this. Well, it's a reciprocal cube of the length of R, okay? Which is like reciprocal cube of A, although it's X that we're integrating with. When you integrate the reciprocal cube of X, you expect to get a reciprocal square, right? So you expect that this integral will produce something with a reciprocal square of A. And you got an A here, and if you divide an A by reciprocal, or multiply an A by reciprocal square of A, you get a reciprocal A. Okay? So the reciprocal A makes perfect sense in terms of dimensional analysis and everything else, and the way antiderivatives of power functions behave. Okay? Again, the point is that the 3/2 power of an x squared is an x cubed. So in a sense, you're integrating something much related to a reciprocal x cubed. You expect to get a reciprocal x squared. When you take the limits into account, you're left with an a cubed, reciprocal a squared. Okay? And yeah, it's, you know, with practice, you learn to see that in integrals, and it's important for understanding relationships and proportionalities, which are key to a lot of applications, especially in engineering. Okay, so there we got it.